Today I'll be describing a technique for running SQL queries faster using deductive synthesis. In this work, we consider the static database use case. Static databases have two key features. First, updates are infrequent, and second, the read performance of the queries is critical. This pattern appears in all sorts of domains, from embedded devices to program analysis. To address this use case, we have developed a tool called Castor, which optimizes the storage of your data on a query-by-query basis. It consists of two key pieces. First, a novel notation that jointly represents the query and the layout of the data that the query consumes. And second, an optimizing compiler for this language. To understand how Castor operates, we can compare it with a standard database system. In a normal database, the user writes a query template, they fill it with parameters, and they send it to the database. The database optimizes the query, executes it, and returns the results to the user in real time. This happens every time the user runs the query. The database needs to be able to answer any query that it receives, so it uses flexible generic data structures. By contrast, in our system, the user gives their query template to our compiler ahead of time. The compiler synthesizes a specialized data structure for each query template using a collection of sound rewrite rules to transform the query. It then generates a native executable for each query and serializes the data into the appropriate format. When the user wants to run the query, they give the query parameters to the executable, which runs the query and produces results. Another way to view our system is from the perspective of the query optimizer. A traditional query optimizer takes a query written in the relational algebra and rewrites it into a form that is more efficient to execute. It treats the storage of the data as a fixed part of the environment, not part of the optimization process. In contrast, you can think of our tool as a query optimizer that is extended, so that it also considers the storage of the data used in the query. Essentially, the responsibilities of the query optimizer are pushed down the stack, so that it considers both the transformation of the relational operators in the query, but also the layout of the data that the query requires. Here we see the query from the previous slide written in our language, the layout algebra. An important feature of our language is that it has three semantic interpretations. First, queries in the layout algebra have a relational interpretation. We can view them as equivalent to a SQL query. We can see there's a correspondence between this filter operator and the where clause in the SQL query, and between this list operator and the selection clause in the SQL query. Second, this program has a layout semantics, which tells us on a byte level exactly how to build a data structure from this query. So there's a correspondence between the list operator and this outer list, between the tuple operator and the tuples inside the list, and between these two scalar operators and the scalars inside the tuples. Finally, this query has a runtime semantics, which tells us how to write code that consumes the layout. So again, there's a correspondence between this filter operator and this if condition, between this list operator and this for loop, and between this tuple operator and this function call. An important feature of these three semantics is that the relational semantics, shown here, is equivalent to the composition of the layout semantics and the runtime semantics. So if we take this layout and we run the corresponding code that reads the layout, we will get results that are equivalent to the results specified by the relational semantics of the query. The goal of our compiler is to generate an executable and a data structure from each query. However, not all queries provide enough detail for the compiler to do this. In particular, a query that does not specify anything about the layout of its data can't be compiled because it doesn't say how that data should be structured. We say that queries that have enough information about their data structures to run through the compiler are well staged. This property is important because the goal of our optimization is to take a query written by the user in the relational algebra fragment of our language, which specifies nothing about the data structures used in the query, to take that query and to transform it using our collection of deduction rules into a query that is well staged and can be compiled. The way to think about this is that we're taking a query and we're transforming it incrementally in a way that does not change its relational semantics, but does change its runtime and its layout semantics. So we're going to start in a position where we have no information about the layout of the data in the query, and we're going to end in a position where we have full information about the data of the layout of the data that the query uses. Now we'll walk through an example. This example is drawn from a tool that my group has developed called Demomatch. Demomatch is a tool for synthesizing code from user interface interactions. It relies on a large database of pre-collected program traces. So these are traces of function calls inside a program. And the queries that the tool makes over this database are known ahead of time. An example query from this system selects calls to a child function from inside a parent function. We can see the query is written in SQL. It selects all of the cases where the parent function ID is equal to a known function ID, the child function ID is equal to a known function ID, and the parent calls the child. So the question that we have to answer is, how should we store this log relation to make this query efficient? Here we see the query from the previous slide rewritten into the relational algebra. We can see the pieces of the original query, the selection of the parent function calls, the selection of the child function calls, and the join, which checks whether the call to the child function happens after the parent function has entered and before the parent function has exited. At this point, we'd like to figure out which data structures might be relevant for improving the performance of this query. One candidate is this join predicate. We have an ordered index, and this join predicate is a range predicate, so it's tempting to use the ordered index to improve the performance of the join. We also have a hash index, and we have two equality filters, and so it's tempting to use the hash index to improve the performance of these two filters. At this point, the question is, how do we introduce these layouts deductively? We'd like to find a transformation sequence that replaces parts of the relational operators with layout operators that implement the same semantics. What we're going to see is a transformation sequence that's one of many possible transformation sequences for this query. Inside our optimizer, we will consider many such transformation sequences and choose the best one using a cost model. For this example, we're just going to show a single sequence. Our first step in the optimization process is to take these two filters and hoist them upwards. This is a standard relational transformation, and in this case, we do it to make it easier to apply transformations that replace the join with an ordered index later. One of the responsibilities of our compiler is to be explicit about the join strategy. Our first step is to take this join and separate out the join filter. What this will allow us to do is to replace this join filter with a lookup into an ordered index. So we'll apply a transformation that replaces the filter with an ordered index. And what we can see is that the original filter selects out all of the enter sub c's that are in between enter sub p and exit sub p. And in the ordered index, we use enter sub p and exit sub p as the upper and lower bounds of the range that we look up in the index. We can see that this ordered index consists of two pieces. We're going to use the values of the enter attribute for keys for the index. So we have one relation that specifies the keys in the ordered index, and this relation has to be evaluated at compile time, so we can construct the data structure. We have a second relation which specifies for each key the corresponding set of values. At this point, we don't have a layout specified for that second relation. Our next step is to use a hash index to improve the performance of this equality filter. To do this, we'll take the filter and we'll split it apart, pushing part of it below the join. We'd like to do this because filtering earlier, before performing the join, will be more efficient. We can use a rule that is similar to the ordered index replacement rule to replace this equality filter with a lookup into a hash index. And we can see that the hash index has a similar structure to the ordered index. It has a keys relation, which specifies the keys in the index. Then it has a dependent value relation that for every key specifies the corresponding values. At this point, we need to specify exactly how these two values relations will be stored. Note that both are unparameterized, so we have a lot of flexibility with what data structure we'd like to use to store them. In this case, we're going to simply replace both of them with row stores. So we have a rule that takes an unparameterized relational expression and replaces it with a list of tuples. At this point, we've fully specified the data structures used in this query. On the left-hand side, we can see a diagram of the data structure that will be produced when we compile the query. We can see that there's a correspondence between each layout operator on the right-hand side and a part of the data structure. So we have the tuple that contains the enter and exit fields, the second tuple that contains the ID and enter fields, the two lists, and the hash index, and the ordered index. In the paper, we compare this layout with two other possible layouts for this query, and we find that this layout is a good compromise between the amount of storage that it requires and its performance. We evaluate Castor on the TPCH benchmark suite, and we compare it against Hyper, which is a state-of-the-art in-memory column store, which has a query compiler that implements some aggressive query optimizations, such as vectorization. We run our benchmark in 4 different modes. First, we run Hyper using its built-in benchmark harness. Second, we provide Hyper with a set of specialized views and indices for each query. This replicates the kind of data specialization that Castor performs, but we must do it by hand, and so we don't get to take advantage of the correctness benefits of using our deduction rules. Third, we choose manually a sequence of deduction rules to run through Castor. So this amounts to manually choosing the data structures that the query will use, but because we use our deduction rules, we have some guarantees that the result that we get is equivalent to the query that we provided. And then finally, we run our automatic optimizer, which chooses a sequence of deduction rules automatically. And what we find is that the specialization of data for the query produces up to 2 orders of magnitude of performance improvement, and that by running our automatic optimizer, which does almost all of the work for us, we can reap most of those benefits. We also compare with Hyper on the size of the data structures that we generate and the amount of memory that running the query consumes. And we find that our implementations of our data structures, because they are highly specialized, give us up to 2 orders of magnitude improvement on both memory use and the size of the data. To conclude, we find that adding layouts to the relational algebra is an elegant solution for specializing data structures to queries, and that this optimization can yield orders of magnitude improvement in query read performance.